Okay, so this is Whitechapel High Street. This is where I work, the Royal London Hospital. As you can see, if you walk down there, you won't really taste or smell anything, but you'll be exposed to very much higher levels of particles from tyres and from exhaust, mainly from diesel. And interesting enough, from what Frank was saying, one of the deaths that was reported during the Great Smog was a young sailor who just dropped down dead outside the Royal London Hospital. And his lungs are, you can see in the museum, if you so wish. This is how we collect particles. You can see the particles. This is an impactor on Marylebone High Street, which is one of the most polluted roads in Northern Europe. And this is what you collect. This is the respiratory range particles. These are less than 10 microns in aerodynamic diameter, so these are not going to be screened out by your nose or your throat and get down into your airways and potentially elsewhere. So these are tyre, brake, some fibres, but a lot of particles from vehicle emissions. They're not round, perfectly spherical things as we saw in the cartoon. They look very, very, very nasty. This is our imaging, more advanced imaging. They have very big surface area, lots of spikes, and that probably increases their surface area and their capacity to interact with airway cells. And this is when we put them onto airway cells. This is just a culture of an airway cell. You can see they get that black stuff gets in quite easily and penetrates. So another way we can see exposure is using bits of kit like this. This is an anethelometer, up to the top left. It's expensive, and it only lasts sort of 24 hours before it needs to be recharged. So that tells you short-term exposure, but unfortunately not longer-term exposure. We've used this for reports, for example, for UNICEF, and this is a typical trace for black carbon. This is the sort of particles which are in the black range. And you can see from this child, he went out playing in the playground, got a spike there in break time, went home, got another spike of exposure, but also a bit at the end, you can see that something happened during breakfast and he got another spike. Now we shouldn't forget about the possibility of indoor generated pollutants and particles. At the global level, we've had instrumented children with asthma in sub-Saharan Africa. Again, you heard about other sources of exposure to particles, and the exposure profiles are very different in these children. So the blue at commute, home and school is for London, and all the others are for the other cities. And you see much higher levels of exposure to particles, in this case PM 2.5, so they're less than 2.5 microns in aerodynamic diameter. And for those children, we've got other sources, not just diesel, but things such as natural dust. Most dusts are outside the respiratory range, but there is a high fraction, which will get down to your lower airway. But other things which are perhaps more tractable, such burning of rubbish and use of mosquito coils and biomass within homes. But of course, a lot of these things are related to poverty and inability to use better forms of cooking. My own attempt at epidemiology, which convinced me particles may be important, was this is a cohort that we had in Leicester, followed up from for 5 or 6 years. I overlaid the council's pollution model. You can see on the left there for the home address, and this is for locally generated particles from traffic, so it tracks with main roads. And despite that sort of relatively crude estimate, we found significant effects for new onset wheezing. So at the bottom, that wheeze, an increase of about 42% increased risk for every micrograms of PM 2.5, but also for cough without a cold, which I think is important because that's bronchitis, and it may be the first evidence of a sort of host deficiency, which could be related to adult onset disease. More recently, with Chris Griffiths, we've looked at lung function cross-sectionally in East London, and this is looking at small differences in exposure in a relatively highly exposed population, with data showing that exposure to air pollution suppresses the growth of lung function. Lung function is various markers that you breathe out forcibly in 1 second, or the total amount of air you can breathe out altogether. There's a common ways we measure that. What we found is one marker of this, forced vital capacity, the total you breathe out, was significantly reduced in children who were exposed to higher levels of pollutant in this pollutant area. And then the good message from that is these are small differences in exposure. So if we make small changes in exposure, we can actually have effects. And the idea about growth of lung function is this sort of idea, is that we're having, we're having tracking of lung function growth. So if you're exposed to air pollution, your growth of lung function is suppressed. So at the top, when you're about 18, you'll have not achieved your normal capacity. And then if your lung function sort of tails off over time. And if you then follow that lower trajectory and move it across, you can see that people who have got adults who have got reduced lung function growth and decline, an accelerated decline, will have lung function which is equivalent to a much older individual. So that's a marker, if you like, of lung aging. And this is important about linking pediatrics and adults. This study, I think, is really important, where it showed, independent of whether the child has respiratory symptoms, looking at subsequent adult bronchitis, and those children who have higher exposure are reporting, as adults, higher levels of respiratory bronchitis. This report I just show is that it's worth looking at, and Stephen may mention it. If you're carrying across here, we can see the same diseases appearing, and we think that in early childhood, and even perhaps as a fetus, some of this is setting the scene for these onset of diseases which are causing mortality and morbidity as adults. Just talking about particles, we saw from Frank that particles are getting taken up by macrophages. We've shown we're using induced sputum. We can look at macrophage loading, and children who have higher levels of macrophage loading, those go over to the right, have lower levels of lung function. Again, this is in Leicester. So this is linking in, providing biological plausibility for this association. Sorry to put you off your lunch. This is an airway lung of an individual where we did a study in Sao Paulo in the autopsy center, and found that actually, you think this is a smoker's lung, but this is a non-smoker's lung. In fact, we found no difference in the amount of carbon particles that we could see at the surface. So these particles are translocated into the surface of the lung. We found no difference between smokers and non-smokers. Smokers have a lot of tar, but particles seem to be the same. And it's just sort of the data that we looked at the surface area of particles. And that's been also shown in the biobank, where the UK biobank, looking at the amount of carbon in lung tissue. Again, no difference between smokers and non-smokers, and particles associated with changes in the VEGF and various other genes which are setting the scene for lung cancer, and certainly non-smoking lung cancer being strongly associated with exposure. I show you this. How do particles get around the body, get to the lung, get to the surface of the lung? One option is they actually stick to red cells, and there's a lot of evidence of people looking for using red cells as a way of delivering therapeutic nanoparticles into the bloodstream. And this is the sort of study here, where if you take out blood cells, put therapeutic nanoparticles into them, it's a very efficient way of delivering particles around the body. And similarly, as with inhaled, those particles will cross into the bloodstream and be transported around the body. Does this happen in real life? Well, in animal models, it seems to happen. This is a red cell with particles on its surface. So we looked at people who were volunteers, willing volunteers, after ethical consent. They spent 4 hours in our institute, went along to the Whitechapel Road for an hour, and we looked at their blood red cells. Standing by the road increased your black carbon concentration, not surprisingly. And when we looked at their red cells, we could see tiny little spots of carbon associated with it. And so, yes, it is. Particles are going into your bloodstream and being transported around around your body. You can do that in a mouse, and you see the same sort of thing. Those particles are fossil fuel derived by various imaging techniques. And interesting enough, the exposure, even 1 hour exposure, results in more particles attached to your red cells. So this is one mechanism that of delivery of particles around the body. So if they go around the body, where do they end up to? I'll show you just to say that as a measure of internal dose, we've looked at whether a mask reduces the number of particles. This is the black carbon between mask and non-mask. Externally, internally, a mask did certainly reduce the number of particles, so maybe a mask is useful. I'll show you. Red cells transport other things, including bugs, so you sort of go off on a different tangent. It's just interesting to see. One organ that comes out of the body is the placenta, so we can get look at macrophages from the placenta. Do they contain particles? Yes, they do. So they contain black little spots of particles, and those are by EDX and various other spectroscopy look exactly like fossil fuel. This is EM showing these little nanoparticle aggregates. So they're getting into the placenta. They are a fossil fuel origin by various spectroscopy techniques, and if you feed them particles, they avidly take them up. So we fed them in vitro. And just recently, we've just been feeding them and looking at interleukin-8 and various other cytokine release, and not surprisingly, they do respond. And interesting enough, we can actually get those macrophages from placental stored in frozen tissue. We've done in Hong Kong and London. So there's potential for biobanking placental material and looking at it later. I'd like to show that, of course, there are other particles, nanoparticles, there's nanoplastics, as you heard, and we do see nanoplastics in various bits of the body. This is recently from New England Journal in bits of endothelium that has been removed at surgery. You can see nanoplastics. I guess they might be transported around by red cells as well. And finally, what are we doing about this? It's all fine. We've been fortunate in London to be funded to do an environmental monitoring clinic where we're looking at children who've got respiratory disease. We actually then instrument their homes, instrument them. Here is a little bit of an instrument that we're using and shows a profile of particles, nitrogen dioxide, and you see spikes, and children have higher levels of exposure. We're feeding back that information to the family to see if we can mitigate exposure. As yet, I think we've got about 70 children, 70 families, and we haven't completed the whole cycle, so hopefully we'll report that at some point. And also we introduce other sort of like an air pollution action plan for those children who've got asthma. So conclusion, pollutant particles, they get everywhere. It's not just in your lung, stay in your lung. They get into tissue, and whether these particles lodging for many, many years, maybe over your life course, are actually causing long-term changes, I think is a big question. I think probably we're going to have to use animal models to answer that question. Because these are relatively low concentrations of particles compared to the lung. We should be thinking about abnormal trajectories. We should be thinking about organ health and maintaining organ health over the life, of course, and intervening early or preventing detriments early, because obviously we see from Frank, the early childhood is very susceptible, but it also is tractable. We can actually make changes, make a difference. Thank you very much.